Okay, we've covered a lot in Chapter 8, and to go over it and expand it just again, and the expansion is the important part. In developing these mid-latitude cyclones, and the surface highs are anti-cyclones, they go in the opposite direction. So, in other words, the surface highs are clockwise, whereas the cyclones are counterclockwise. You've seen already that the upper level waves are very important to the cyclonic development and strengthening. And you've seen that these are surface lows that can extend up to the stratosphere, that certainly intensify with height, and that are dependent on convergence and on divergent air. I wanted to say what these cyclones are not, because it's also important. If you had a surface low with converging air topped by an upper level low, that would not sustain a strong storm, because a surface low topped by an upper level low does not have the diverging properties that the upper level needs. In other words, this would be in the upper level converging, and this would be at the lower level converging, and there would just be so much air that this would no longer be a low pressure situation because it had so many molecules of air there. So a surface low topped by an upper level low, never going to work for a strong storm. Never going to be a storm, really. A surface high topped by an upper level high is never going to be fair weather, because you will never be able to sustain this surface high unless you keep putting air into the surface high to move it out. If you have a diverging high in the upper level, you're not supplying anything down to the lower level. So it's important to know what cyclonic storms strengthen with, and it's also important to know what cyclonic storms die from. Just to go over again, best case scenario, to the east, a surface low. Right above, a little to the west, an upper level low. Even more to the west, a surface high. That really maximizes the strength of the trough in the upper levels and the converging air that can sink right down into the surface high, and the diverging air that can suck everything out of the surface low. Just to go over, if you need another way to look at it, to make a low pressure at the surface stronger, you need upper level divergence. To make a high pressure at the surface stronger for great weather, you need upper level convergence, right? And I wanted to go over how this all comes together at the surface. So let's go from the upper level down to the surface. You have a convergent flow to the west of the trough. You have a divergent flow to the east of the trough. And then when you come down here, that convergent flow will head right into a surface high. And you will find that that surface high is driving the cold front. So when that cold front comes in, you'll find showers along that area as the Cadillac is busting in and throwing the Volkswagen, the warm air up above. You'll have showers in that area. You have a warm sector that is fueling the low, which is converging air around it and sending that air up to the divergent air above. Things get complicated at this warm front because you have in that area warm air that is above cold air and is producing snow, sleet, rain. So this area to the east of the low is getting a lot of precipitation from the warm front and the cold front that will come through later. And the air that's in the northwest quadrant will get the snow from the occlusion and all of the warm sector air that goes up and then goes in a 3D position sitting on top and swirls in here to form that cyclonic motion and dump a lot of winter snow there. To look at where this comes into play, this is about the 50-degree mark during the wintertime in the northern hemisphere. So we've got two semi-permanent lows in that area that are starting out the lows that we are thinking of for cyclonic action. Those two lows around the 50-degree mark can spread out into other lows. And you've got in here the Aleutian low, which is also the Gulf of Alaska low, and one that you might have heard of, an Alberta Clipper. Remember, these are right around the 50s and the 60s, 50s because they moved south a little bit in the wintertime. And those are natural lows in the area because it's the polar cell and the Ferrel cell. These other lows are a little bit different. The Colorado low actually comes right out of the Chinook winds and the rain shadow. So that rain shadow came down and compressionally warmed right in Denver. Well, that warm air continued east, and that warm air rising slow, remember? Clouds and snow, surface low. So as the compressional warming sits down in east of the Rockies, it'll start to rise again and form lows that can head in here. The Gulf lows are from the warm, moist air out of the Gulf, especially during the winter. The Hatteras low is from the warm, moist air from the Gulf Stream, which is a very big player for us in the winter as well. These lows are steered by the surface highs that are in place up in the polar regions, so that these highs can come down during the winter and steer the lows. Remember, the high pressure pushes. The lows wouldn't go anywhere without the high pressure pushing it. Now, we've learned about the jet streams and how important they are, and I want to extend from the jet streams that you know to the other wind streams that are not as fast as the jet stream, but very important. So the jet stream is part of the upper level waves of air, just very fast, and other upper level waves move more slowly, but they're very important as well. Those are known as long waves or Rossby waves, very well studied by the researcher Rossby. At any given time across the world, circulating temperatures in the upper levels, there are 3 to 6 Rossby waves. These waves cover thousands of miles, obviously. Here's an example of one down here. This is a slate trough there that you see associated with a semi-permanent low, a slate trough, a slight rise, and then another slate trough. So a wave goes from trough to trough, or just like a frequency, from a ridge to a ridge. And the troughs are associated with semi-permanent lows. The ridges are associated with semi-permanent highs. Pretty easy to understand. They're very slow to move, and they are actually the foundation for the Farmer's Almanac. When you look at the Farmer's Almanac predictions, they're based on the long waves in the atmosphere, because they can do that a year in advance. They move that slowly. On the other hand, short waves, there are scores of them across the world at any given time. They're quick, they move fast, sometimes within 12 to 24 hours, and they are hard to predict. You might say, well, what causes the long waves and what causes the short waves? The long waves are caused by the gravitational movements and the tidal movements of the moon and of the gravitational pull of the moon. So that is really an important part of the long waves. The short waves, we need a lot of research into. In some cases, we're thinking that it is tied to global warming and that the short waves may be getting more pronounced at this time. But the short waves are important because they deepen the long wave troughs, which are pretty gradual in the long waves, and they accentuate the long wave ridges. So you see this here. Here's our little gentle trough, but it becomes more than a gentle trough when it has a short wave trough associated with it. The short wave deepens the trough and it pushes the ridges so that they become more pronounced as well. Now, I'm going to move to the next slide because I want to show you something. When there's no short waves in the area, the long waves really go very, very well with the temperature gradients in the upper levels. So you see how the middle of the temperature gradient is right in between the long waves. And that's very predictable. And then I want to show you something, and then I'll come back. When you throw the short waves in here, it wrecks up your nice, predictable long wave. See, there's a long wave with the temperature right in between. It's getting a little wrecked by the short waves, but not very much. Look here. The short waves have really wrecked up the angles of the temperature gradients. Let's explore what this means for cyclonic motion and what this means for powerful storms, maybe for global warming too. When you have the second step of cyclogenesis, the frontal wave, and you have a short wave that has caused that frontal wave, remember, because it nudges down that cold sector of the stationary front by a short wave. Well, that short wave deepens a trough, and it actually forces the cold temperatures down into the converging air that goes down into the surface high. So that's what produced that surface high that nudged down and started that cold front. It was formed by that short wave that pushed this cold air down when it wrecked up those nice gradients. And conversely, now I've got a warm front that is sending warm air up into the upper atmosphere and further wrecking those nice, even temperature gradients. So you can see where global, climate change might impact these short waves, and they feed off of each other. When it comes to the cutoff low section, you've actually got a short wave that has moved east now. Here it is here. Now it's farther east, right? So it's no longer to the west of the surface low. It's right on top of the surface low. And remember, we said a surface low topped by an upper level low does not go together well. That will just break the entire storm apart because there's no longer any divergence up here to take off everything that's coming into this surface low. Suddenly your surface low becomes a high pressure area because it's got so many molecules of air in there. So I wanted to go over that with you because in summary, Chapter 8 is an important one. Different air masses, different fronts, and different stages of cyclonic motion. Go over it all, and we'll get to Chapter 9, which is a lot shorter.